Alright, this problem says a string of length 5 meters and a mass 90 grams is held under tension of 100 newtons. The wave travels down the string that is modeled as yxt equal to 0.1 meters sine 0.4 x minus 1170 seconds. Well, there's a t missing there. What is the power over one wavelength? Okay, so I've written down the expression for the power ahead of time. Okay, so let me rewrite this equation and we'll check a couple of things for consistency. Xt equal to 0.01. Everything is in SI units, so I won't write units down to avoid clutter. Minus omega t. Okay. So here's the amplitude, here's the wave number, and here's the angular frequency. Okay, I meant to write 1170.1 t. Okay, and now we'll do a consistency check. The velocity is omega divided by k, but it's also related to the mass per unit length and the tension in the string. So velocity is omega by k, and this should be 1170.1 1/seconds divided by 0.4 1 meters, and so this should be, this is 1170.1 divided by 0.4. The velocity of the wave is 2,925.3 meters per second. And let's see what the velocity of the wave is according to this formula, tension divided by mu. Mu is the mass per unit length, which is 90 grams, 10 minus 3 kg, divided by 5 meters. And 5 divided by that is 90 divided by 5, 18 into 10 minus 3 kg per meter. Okay, so velocity according to this formula would be, the wire is under 100 Newton tension, 18 into 10 minus 3 kg per meter. Okay. So let's 0.1 divided by 18, and you can see that these two velocities, this velocity and this won't agree, so there's some inconsistency. There's some inconsistency in the problem. Okay, but oh wow, this is crazy. So this is this says 74.5 meters per second. All right, so is there a fix? 0.7 divided by, all right, so we could fix this inconsistency if this were 29.8. All right, so I'm going to fix that. All right, so let's fix this problem. We'll add a page. So we will rework this problem assuming xt is equal to 0.1, right? 0.01 sine 0.4x minus omega should be 29.8 t. Okay, so we've changed omega to 29.8 1/2. Okay, now let's get to the power equation. So the power equation is 1/2. So what we're saying is this velocity is wrong from, so we've changed that. Okay, so let me, I can mark this. These two numbers are wrong. Have been changed. Okay. Being changed. Okay. They're not consistent with these two numbers. Okay. So we're solving the problem assuming these two numbers are correct, or yeah. So we'll solve it using those two numbers. All right. So power is 1/2 mu. The power is energy traveling down the string per second is 1/2 mu v omega square a square. Okay. So mu v omega square a square. Okay, again, the quantities are mu is mass per unit length, v is the velocity of this of the wave on the string, and omega is the angular frequency, a is the amplitude of the wave. Okay, so let's put these numbers down. Mu is 18 times 10 to the minus 3 kg per meter. Velocity of the wave is, here's the velocity of the wave, 74.5 meters per second. Omega, here is omega consistent with the tension and that, so 29.8 square, and amplitude is 0.01 meter square. Alright, so now if we calculate all of this, let's take care of powers of 10 first. This is 10 minus 2, 10 minus 4, 10 minus 7. So there's 10 minus 7. And this is power, so it would work out in watts. So now let's do the other parts. Half times 18 times 74.5 times 29. Oops. 29.8 squared. Okay. Alright, so this works out to 59.5 milliwatts. Okay, so that does that problem.